shot. The routine, number one, helps relax me, and it also gives me a chance to get some air. And
for this lab, I had to look up the diameter of a basketball, which I found to be 9.3 inches, and I used this data to track the path of the ball in the basketball court. As you can see, when I graphed the data, it appeared just as I thought it was, in a parabolic shape. Also, here you can see I modeled the action on VPython as well, and it also produced a parabolic shape. I also put 3 arrows. The red arrow labels the momentum of the ball, the white arrow labels the force, and the blue arrow labels the perpendicular momentum. Since I knew the diameter of the basketball was 9.5 inches, I was able to use this to find the initial position of the ball, which was 0 in the x direction and 2.48 meters in the y direction. Using this, I was also able to determine the initial velocity vector, which is 3.39 meters per second in the x direction and 4.93 meters per second in the y direction. The constants used when creating this VPython code was the ball mass of 0.6 kilograms, gravity was 9.8 meters per second squared, and I found the air density near the surface of the Earth to be 1.3, the area of the ball I calculated at 0.1753, and I looked up the drag coefficient of a basketball, which is around 0.25. Looking at this page, you can see how I calculated the different physical components of the ball. I calculated the net force on the ball, as well as updating the momentum, the position, and the trail of the ball. Once I finished writing the code, I was able to calculate all the different components. I know the total time took 3.19 seconds. The magnitude of the ball velocity was 20. And I also calculated other components such as the x velocity and y velocity, the final position, the magnitude of the parallel forces and perpendicular forces. And I also have the radius of the kissing circle.